Welcome back to the deep dive. Ready to explore something pretty mind-bending today? We're diving into NP-Completeness. You know, that thing that keeps computer scientists up at night.
You got it. It's basically the ultimate challenge of computer science. Can every problem whose solution is easy to verify also be solved quickly?
That's the million-dollar question, right? P versus NP. It sounds simple, but it has huge implications for everything from cryptography to artificial intelligence.
Exactly. Cracking this could revolutionize how we solve all sorts of problems, or, maybe it'll prove that some problems are just inherently difficult, no matter how powerful our computers get.
Either way, it's worth exploring. So for our listeners who maybe haven't spent their days wrestling with algorithms, let's start with the basics. What exactly do we mean by polynomial time?
So in the simplest terms, an algorithm runs in polynomial time. If the time it takes to solve a problem grows at a rate that can be described by a polynomial function of the input size. Think O, n squared, that sort of thing.
Right, like if doubling the input size only quadruples the runtime, that's polynomial. But if it, say, squares the runtime, that's not. And generally, polynomial time algorithms are considered efficient.
Yeah, for the most part. Of course, in practice, an algorithm with a really high-degree polynomial might still be too slow to be practical. But as a rule of thumb, polynomial time is good.
It's kind of like the sweet spot for computational complexity. And thankfully, as our sources point out, most real-world problems that are solvable in polynomial time don't have crazy high degrees.
Right, usually it's something manageable. And another nice thing about polynomial time solvable problems is that they play well together. If you combine a few of them, the resulting problem usually stays within that polynomial time bound. It's a pretty well-behaved class of problems.
Okay, so that's polynomial time. But to really get into NP-completeness, we need to talk about how problems are formally defined in computer science.
Right. Often an abstract problem is defined as a relationship between instances of that problem and their solutions. Like, given a map, what's the shortest route between 2 points? But when it comes to NP-completeness, we mainly focus on decision problems.
Decision problems, meaning problems with a yes or no answer.
Exactly. Things like, does this graph have a Hamiltonian cycle? Or can this Boolean formula be satisfied?
I see. So instead of asking for the best solution, we're just asking if the solution exists.
Precisely. And it might seem limiting at first, but it turns out that many optimization problems, those where you're looking for the best solution, can be rephrased as decision problems.
Okay, I think I get that. So like instead of asking what's the shortest route, you ask, is there a route shorter than X miles?
Exactly. And then, to actually work with these problems on a computer, we need to encode them into binary strings, just zeros and ones.
Makes sense. Computers basically speak in binary.
Right. So the concrete problem is one where the instances are already given as binary strings. And if there's a polynomial time algorithm that can take that binary string as input and spit out the correct yes or no answer, then we say that concrete decision problem is in P.
Okay, so key is like the realm of problems we can solve efficiently. But wait, I remember our sources mentioned something about how the way we encode a problem can affect whether it seems to be in P or not.
Ah, you're thinking about encodings. And you're right. Technically, if you use a really weird, inefficient encoding, you can make an algorithm look like it's running in polynomial time when it's not really.
Like tricking the system?
In a way, yeah. But for our discussion, we're assuming reasonable standard encodings, things that can be converted between in polynomial time. So if a problem is solvable in polynomial time with one of these encodings, it'll be solvable in polynomial time with any other reasonable encoding.
Gotcha. So no sneaky tricks allowed. We're playing fair here.
Exactly. And there's another way to look at all this, too. You can think about decision problems in terms of formal languages.
Formal languages?
Yeah, like think of a language as a set of all the yes instances for a given decision problem, represented as binary strings.
Okay, so the language of, say, Hamiltonian cycle would be the set of all graphs that actually do have a Hamiltonian cycle, encoded as binary strings.
Exactly. And then the complexity class P, instead of thinking about it as problems that can be solved in polynomial time, we can think of it as the set of all those languages that can be decided by a polynomial time algorithm.
So an algorithm decides a language if it can tell you, for any given string, whether or not that string belongs to the language. Basically, it's the algorithm saying yes if the string is in the language and no if it's not.
Exactly. So that's P, the set of languages that have a fast membership checker, so to speak. Now let's step into the world of NP.
This is where things start to get really interesting, right? Because NP isn't just about solving problems quickly. It's about verifying solutions quickly.
You got it. NP stands for non-deterministic polynomial time. But that non-deterministic part can be confusing. It's not about randomness. It's more about this idea of a magical computer that can explore all possible solutions at once.
Okay, so maybe not something we can build in the real world.
Probably not. But in a more practical sense, NP is all about those decision problems where if the answer is yes, you can verify that yes quickly if you're given a little extra help.
That extra help being the certificate, right?
Exactly. The certificate is like a proof. It doesn't tell you how to find the solution, but it lets you quickly check if a proposed solution is correct.
So, for example, if we're talking about the Hamiltonian cycle problem, the certificate would be the actual cycle itself, the sequence of vertices.
Right. And you can check if that sequence really does form a Hamiltonian cycle in polynomial time. Just follow the path, make sure it hits every vertex exactly once, and that every step is a valid edge in the graph.
And for 3CNF satisfiability, which we touched on earlier, the certificate would be a specific assignment of true and false values to the variables that makes the whole formula true.
Exactly. You can plug those values in, do the calculations, and see if the formula holds true, all in polynomial time.
So the key thing about NP is that even if finding the solution might be really hard, checking a solution, given the right certificate, is easy. And it's important to note that this certificate can't be ridiculously long. It has to have a size that's polynomial in the size of the input too, right?
Absolutely. Otherwise, the verification wouldn't be considered efficient.
Okay, so now we've got P, where we can solve problems quickly, and NP, where we can verify solutions quickly. And it makes sense that any problem in P is automatically an NP.
Right. If you can solve it quickly, you can certainly verify a solution quickly too. You just solve it yourself and compare. So P is definitely a subset of NP.
But the big question is, are they the same? Is there some clever way to find solutions for every problem in NP just as fast as we can verify them?
That's the P versus NP question. Yeah. And most computer scientists believe the answer is no. They think there are problems in NP that are just fundamentally harder to solve than to verify.
And our sources bring up this other class, co-NP. What's that all about?
So co-NP is like the flip side of NP. It's the class of problems where if the answer is no, you can verify that no quickly given certificate.
Okay, so like for the Hamiltonian cycle problem, co-NP would be about proving a graph doesn't have a Hamiltonian cycle.
Right. And a big question here is whether NP and co-NP are the same thing. If you can quickly verify a yes, does that mean you can also quickly verify a no?
And the answer is, we don't know.
Not yet, at least. It's another one of those big open questions in complexity theory.
So we've got PNP and co-NP, and we know P is a subset of both NP and co-NP. But whether it's a proper subset of their intersection, that's still a mystery.
It really highlights how much we still don't know about the landscape of computational complexity.
All right, so we've laid the groundwork. Now let's get to the heart of the matter. NP-Completeness. And this all hinges on this idea of reducibility, right?
Exactly. Polynomial-time reducibility. It's how we compare the difficulty of different problems. We say a language L1 is polynomial-time reducible to a language L2 if there's a function that can transform any instance of L1 into an instance of L2 in polynomial time, and the answer to the L1 instance is yes, if and only if the answer to the corresponding L2 instance is also yes.
Okay, so it's like we have this magic translator that can convert one problem into another without changing the answer, and this translation has to be fast too.
Exactly. The algorithm that does this translation is called the reduction algorithm. And the important thing is that if we have this polynomial time reduction from L1 to L2, and we can solve L2 in polynomial time, then we can also solve L1 in polynomial time.
Because we just translate the L1 instance into an L2 instance, solve the L2 instance, and we know the answer will be the same for the original L1 instance.
Precisely. And this leads us to the definition of NP-complete problems. A language L is NP-complete if it satisfies two conditions. First, it has to be an NP itself, meaning we can verify yes answers quickly. And second, every other language in NP has to be polynomial time reducible to it.
So NP-complete problems are like the hardest problems in NP. If you can solve one of them quickly, you can solve them all quickly.
Exactly. And then there's NP-hard, which is similar, but it doesn't require the problem to be an NP itself, just that everything in NP can be reduced to it.
So NP-complete problems are a subset of NP-hard problems.
That's right. The set of all NP-complete languages is often called NPC. And here's the really important part. If we find a polynomial time algorithm for even one NP-complete problem, then it means P equals NP.
Because everything in NP can be reduced to that NP-complete problem, and if we can solve that quickly, we can solve everything in NP quickly.
Exactly. And the flip side is also true. If we can prove that even one problem in NP can't be solved in polynomial time, then no NP-complete problem can be solved in polynomial time either.
So NP-complete problems are like the key to unlocking the P versus NP mystery.
They are. And the first problem that was proven to be NP-complete is circuit sat, the circuit satisfiability problem.
Circuit sat. What's that?
It's about Boolean circuits, those things made up of logic gates like AND, OR, and NOT. The question is, given a circuit, is there some combination of inputs that will make the output true?
So, like figuring out how to set the switches to turn on a light bulb at the end of a complicated circuit?
Kind of, yeah. And circuit sat is an NP because if you're given a set of inputs that supposedly satisfy the circuit, you can easily check if that's true by just simulating the circuit and seeing what the output is.
Okay, so that's the verification part. But how do they prove that every problem in NP can be reduced to circuit sat? That seems really hard.
It is. The proof is pretty involved, but the basic idea is that you can represent any polynomial time verification algorithm as a sequence of configurations of a theoretical computer. And then you can build a circuit that simulates those configurations and the transitions between them. So for any problem in NP, you can build a circuit that will output true if and only if there's a valid certificate for that problem.
Wow. That's pretty mind-blowing. So circuit sat was the first domino to fall, and then researchers figured out how to prove that other problems are NP-complete too.
Right. And the way they usually do that is by reducing a known NP-complete problem to the new problem. Yeah. Because polynomial time reducibility is transitive. If you can reduce, say, circuit sat to a new problem, and you already know that everything in NP can be reduced to circuit sat, then everything in NP can also be reduced to the new problem.
It's like building a chain of reductions, linking problems together by their difficulty.
Exactly. So our sources go through a few examples of these reductions, like how to reduce from circuit sat to SSAT, which is the satisfiability problem for general Boolean formulas, not just circuits.
And then from SA to 3CNF SA, which is satisfiability for formulas that are in a specific format called 3-conjunctive normal form.
Right. 3CNF SAT is important because it's a restricted version of SAT, but it's still NP-complete. So it's often a good starting point for proving that other problems are NP-complete.
And then our sources go through a bunch of other NP-complete problems like CLIQUE, VERTEX-COVER, ham cycle, TSP, and subset sum. It's amazing to see how all these seemingly different problems, from graph theory to number theory, are all connected by this idea of reducibility.
It's like they're all different sides of the same coin, computationally speaking.
Right. And understanding that a problem is NP-complete is really important in practice because it tells us that we probably shouldn't waste our time trying to find a perfectly efficient algorithm for it.
It's a sign that we should focus on other strategies, like finding approximate solutions or good enough solutions, or maybe trying to identify special cases of the problem that are easier to solve.
Okay, so as we wrap up this deep dive into NP-completeness, what are some of the key takeaways for our listeners?
Well, I think the biggest one is that the P versus NP question is one of the biggest unsolved problems in computer science. And it has profound implications for how we understand computation and the limits of what we can solve efficiently.
And even if we don't know the answer to that question, just understanding the concept of NP-completeness and the interconnectedness of these difficult problems is incredibly valuable.
Absolutely. It gives us a new lens through which to view computational problems, and it helps guide our research and development efforts.
So next time you're struggling with a particularly difficult problem, take a moment to think, could this be an NP-complete problem in disguise?
It might just be that the difficulty you're experiencing is inherent to the problem itself, not a reflection of your own abilities.
And who knows, maybe someday someone will crack the P versus NP puzzle and change the world of computing as we know it. Until then, the deep dive continues.